result is a global existence result, which can also be seen as a stability result for the trivial solution of the problem of choice. And the outline of my talk here will start with an introduction where I go into the history that builds up to the problem we are treating, the literature review to motivate a few things about the nonlinearity we have chosen, involving a power function beside a logarithmic function and an integral term. Then the problem statement, preliminaries and the setting of the problem, and then we go into the theorems of existence and uniqueness. So in the introduction, I'll start with simple heat diffusion equation in one dimension, R, with initial data as the delta function. And we know that following Fourier transform methods, the solution has this form, which is greater than 0 strictly for all t greater than 0. Now, what this means is that you start with an initial data which is concentrated at a point, and then instantaneously the entire domain is covered by the solution, meaning that an element in the domain, no matter how far it is from this concentrated source initially, will feel a disturbance in temperature instantaneously. Now this is a defect actually, because it violates the principle of causality, which says that no signal should propagate faster than light. Now, this problem is not just restricted to initial data that are delta functions. We see here an example from a book by Richard Haberman with an initial data that's not continuous. And this phenomenon of infinite propagation is illustrated in the graph here, where you see the left side, which initially is completely 0, instantly bumps up over the entire domain, no matter how large the domain is. So what does this lead to? This property renders the diffusion equation actually to be an undesirable model under certain conditions. Like I mentioned before, under relativistic considerations, where the speed limit of the universe is the speed of light, this violates the principle of causality because it's actually propagating at the speed of light, which is infinite. Now, this is not just the only consideration that makes the diffusion equation undesirable in some sense. In 1917, there's a work by Walter Nernst on the thermodynamic behavior of systems when the temperature is almost negligible, near absolute 0, that is. So Walter Nernst discovered that heat capacities, when the temperature is near absolute 0, heat capacities tend to 0. But heat capacities are proportional to heat energy, which is responsible for propagation. Now, vanishing heat capacities mean that you have very little heat energy, though it's enough to raise the temperature of an element, but it's too little to support infinite propagation. So at temperatures near absolute 0, you can only have finite speed propagation. So in this case, other models are preferred to the usual diffusion equation. And this statement is what I'm saying: extremely low heat energy does not support infinite propagation speed. So there's another scenario where the heat equation is not the preferred model for heat transfer. In large domains, sometimes hyperbolic models are prepared. For example, there's a work here in 3 using lasers on a semi-infinite medium. And over there, they suggested a hyperbolic model, which appeared to be actually a more accurate description of the phenomena they were trying to describe. Then there's also the phenomena of second sound propagation, which is what heat is called when it's modeled by a hyperbolic equation. In moving media, this is a work that I've read a few times. This hyperbolic equations are also more preferred sometimes when modeling non-homogeneous media or media that has memory, heat memory. So now that we have seen the defect associated with the heat equation under certain conditions, there are others that have worked on how to rectify this defect. And among those, there's actually James Maxwell and Vanotti, but Cattaneo is much more referred to. So among those that tried to rectify the problem of infinite speed propagation is Cattaneo, who suggested this model instead of the Fourier model. Because as Nance discovered in his work, the problem was coming from the Fourier heat conduction. So replacing the Fourier heat conduction with Cattaneo's model leads to wave equation, basically, which we know has finite propagation speed. So in this work, after seeing all this, we will borrow the idea of Cattaneo and will apply it on a fractional diffusion equation, which is known to possess infinite propagation speed. You can see, for example, the work of Mokhtar and Fino, lemma 3.2. You will see this property. So what we will do for this fractional diffusion equation is to add a correction term similar to Cattaneo's, which is oscillation, making it a wave equation. And on the right side, we see the fractional diffusion, which I've mentioned. Only that part has infinite propagation speed, but now we borrow the idea of Cattaneo to consider a fractional wave equation. For the nonlinear term, of course, it's non-local. We are considering integration from 0 to t. So the value of the operator on the left at time t depends on the value of the integrand starting from 0 up to t. But for the motivation, I'd like to leave this part to the literature review. Now in this talk, we have a few objectives as promised in the abstract. Though the main point is about global solutions, a long-time behavior, which here I mentioned as the key estimates. In the abstract, I also promised to talk about norm estimates of the linear problem and local mild solutions in an appropriately defined functional space. So now with the literature review, I should mention that in most of the literature, when talking about global existence, there's another side to the problem, which is the blow-up side. Though in this talk, my objective is not to prove blow-up, but the literature would be incomplete without mentioning the contributions of the blow-up problem, especially to how these nonlinearities look like. So I'll start with the work of Osgood, who established blow-up solutions for ordinary differential equations of the form derivative of u in time equals f of u, initial data non-negative and the nonlinear term positive. In this case, Osgood found that blow-up occurs if and only if the integral condition here holds. Now, looking at this integral condition, we can see that for the choice of power functions, for instance, which is mostly the case in the literature, you'll have that the exponent of the power function, say p, if we call it p, will have to be greater than 1. But not only power functions satisfy this in the literature, you can see exponential functions, though power functions are more common recently. And this can be seen in also the classical work of Fujita on the heat equation. As you can see, his choice of the nonlinear term here is u raised to the power of 1 plus alpha. Alpha strictly greater than 0, so that you can see some connection to Osgood's previous condition. Here, Fujita was interested in blow-up for non-negative solutions of the reaction diffusion equation. And this blow-up problem and global existence are connected to the behavior, or I should say are connected to the nature of the domain and the behavior of the exponent. In this case, Fujita found that if the dimension of the domain times the exponent, the alpha is less than 2, then every non-negative solution blows up, of course, except the trivial solution. And if in the opposite case, m times alpha is greater than 2, then there are numerous non-negative initial values that lead to global solutions. Now, the next work I'd like to present, though not as earlier done as Fujita's, is a work on the wave equation. And still, it's kind of following Osgood's condition in choosing the nonlinear term. So you have absolute value of u to the power of p, non-negativity, p greater than 1, and you have the damped wave equation. The initial data here, you see an epsilon attached to u0 and u1. In this case, the idea of Todorova and Yordanov is to use this epsilon as a smallness parameter because that's what we usually do. We need some smallness of the initial data for the global existence. And he picked this initial data to be compactly supported. Then he showed that solutions are global when the exponent is greater than 1 plus 2 over n, which is, this is usually referred to as the Fujita exponent in the literature. And you have blow up in the opposite case. Now, I forgot to mention that in both the case of Fujita and Todorova here, the critical exponent belongs to the blow-up regime actually. So when here P is less than or equal to PCN, you will have blow-up of solutions. The next work I am presenting here is on the fractional diffusion equation, where diffusion is governed by fractional power of the Laplacian. This work was done by my professor, Mokhtar Kirane and Ahmed Fino, his former student. And the idea was also to prove blow up in the subcritical range, that is less than or equal to the critical exponent, and to prove global existence when the exponent of the nonlinear term is greater than the critical exponent. However, in this case, as has been the case recently with this type of non-local nonlinear terms, you see that there is an effect of both the exponent of the nonlinear term and the kernel in here, which is a bit singular. You see the critical exponent contains 1 over gamma. This is to take into account the effect of this singularity. So the result here was that there is a global solution for this problem for initial data small enough, in the sense that the initial data U0 is in C0 of Rn intersection LQ. Then for P greater than the critical exponent, there's a global solution. However, the opposite occurs for P less than or equal to the critical exponent. Irrespective of the smallness of initial data, you have blow up in this case also. The next problem of interest here is also the work of Fino on damped wave equation, with also a non-local in time nonlinearity. Here U0 and U1 are taken to be the initial data, but the global existence result obtained for dimensions between 1 and 3 is not in the entire supercritical range, meaning that if you look at the exponent of the nonlinear term, you have global existence, but for P greater than some Pn. In each dimension, there's a number referred to as Pn, P1 in dimension 1, P2 in dimension 2, P3 in dimension 3. These numbers separating the exponent of the nonlinear term from the critical exponent. So this left a gap as far as global existence was concerned. However, in the blow-up case, you have blow-up for the entire subcritical range, P less than or equal to the maximum of this critical value. So because of the hole left by the global existence in the work of Fino, Dabiko, on his paper concerning the influence of non-local memories on global existence solutions, he filled this and he showed that we have still global existence in the case that P is strictly greater than the critical exponent in the entire supercritical range. So our results are similar in approach to the work of Dabiko and Fino, and sometimes in the proof of the result, I refer to a lemma in their preliminaries because it's just a substitution over it. Now, as to our nonlinear term, we have this non-local part also, and we have this kernel, which is singular. However, instead of only u to the power of p, we have some powers and a logarithm beside them. Now, as far as we have seen in the literature, the first work concerning this type of logarithmic nonlinearities is due to Sobolewski and Yasarkov, working on global existence for parabolic equations with this type of growth assumption on the nonlinear term. After them, there was a work of Berula and Masielski on nonlinear wave mechanics, where their interest was first to find nonlinear terms that will give the nonlinear Schrodinger equation soliton-like solutions. In the end, Berula and Masielski discovered that the good nonlinear terms in that case are those of the logarithmic form. There's also the work of Kazanov and Haru on global existence for wave and Schrodinger equation containing a similar nonlinear term with the power function beside the logarithmic. But all of these works do not concern non-local in time nonlinearities. Now we have reached a point to describe our own problem. So compared to the works that we have seen and the motivations, we are interested in the global existence problem for this equation. Epsilon in principle should be small since we are following Catania's idea, but we allow it to be equal to 1. So we can cover the wave equation of Venus, for instance. And here is our nonlinear term, non-local in time, singular kernel, p strictly greater than 2, so that we keep in line with the condition of Osgood. So we can talk about blow up. We keep the parameter beta to be greater than 1/2. We'll see that we are restricted here because of issues like the Sobolev embedding theorem. The parameter alpha is strictly less than 1 here and greater than 0. This is also useful, as we'll see in the application of Grunwald's lemma, for instance. And as I've mentioned, our strategy is similar to the work of Dabiko and Fino. So I will state once more our objectives. I'll talk about the norm estimates of the solution of the linear problem. I'll give a brief idea of the proof, since we followed a similar way as Matsumura did in his work on Matsumura's estimate. Then I'll talk about the local solutions. I'll give more details here on local solutions because the argument is by the Banach contraction principle, and it's a similar argument for the global solutions. Only a few changes are needed, and then we just apply a lemma from the work of Fino. So I'll start with tools here and explain where we use each one. This is a lemma of Plancherel. It is particularly important because we will be taking the definition of the fractional Laplacian here in terms of the Fourier transform. So when, for instance, we reach the lemma of norm estimates, we'll be using this one to control our norms. Then Holder's inequality. This will be particularly important when using the Banach contraction principle to prove contraction mapping. So the next is the contraction mapping principle. This is here just for a reminder. So the point here is the first point. We'll be applying the contraction mapping principle on a closed ball. It is more convenient to go that way. Then for uniqueness, we have here a classical weapon fashioned against the uniqueness problem, the famous Grunwald's lemma, where you have mostly the functions in L1, integrable in time, g of t and h, and the product of g and h. And two constants C1, so you get g of t is controlled by C1 exponential of the integral of h times some constant. In this case, we will use Grunwald's lemma, but our g and h will have the form of a norm. Our g will have the form of a norm, sorry, but h, we'll see that it's our kernel as seen before. So here is the local solution setting. We'll take our initial data, the phi u at x at time 0 will be in h beta intersection L1, derivative of u in time, at time 0 will be psi in L2 intersection L1. And we define the space H beta as the Sobolev space of functions G in L2 of Rn if beta is a natural number, or the tempered distributions if beta isn't a natural number. And we define the norm using the Fourier transform. This is one of the ideas here we use with Plancherel. So we use the Fourier transform definition for the norm. With the local existence theorem, we see the first effect of our adding our logarithmic term to the nonlinear term in insisting that P is greater than 2. And with this insistence, and that n divided by n minus 2 beta is greater than 2, we are restricted actually to dimensions 1, 2, and 3. So for our initial data in the space H0, which is defined as the product of the spaces in equation 10, we claim that there exists a maximal time and a unique mild solution. We'll see soon what a mild solution is, such that U is continuous in time into H beta and C1 in time into L2. Moreover, we have the alternative that U can only behave in one of two ways. Either U is global, in which case T max is infinity, or U can only remain local because it blows up in a finite time, T max finite, and these norms blow up. So this is part of the idea of the local solution, but the norm estimates are important for both the local solution and the global solution. So we'll start with the solution representation to see how we estimate these norms. So starting with the linear part, ignoring the nonlinear part, we have the linear solution can be written in this form. UL, that's the linear solution, is equals U1 with this convolution in space, and UA, an auxiliary function. But U1 is defined basically as the fundamental solution. We have U1 at 0 will be 0. The derivative of U1 in the Fourier domain will be 1, like the delta function. So that defining them by Fourier transform, the Fourier transform of U1 is of this form. Here we clearly see the effect of epsilon, the oscillation term. You see that when epsilon goes to 0, in the cases in equation 12, you will have only a solution with sign. So when epsilon goes to 0, basically we are thinking we only have the fractional division. And the sign you see is not a function that vibrates that much. You only have low frequency as expected of diffusion. However, if epsilon is not 0, you have the solution will have two parts of low frequency and high frequency with the sign functions vibrating for the frequency. So we put together what we call a mild solution using Duhamel's principle. We define it by taking the solution of the linear part, the homogeneous solution, which we call UL. Then we add a particular solution. This is from Duhamel's principle, where you convolve in space and time with the nonlinear term. Now we come to our norm estimate for the linear solution, and we claim this lemma, assume that psi, which is the initial data for the derivative in time, is in this space, 1 less than or equal to r less than or equal to 2. Then we combine here, depending on value of k and the multi-index tau, you have a decay of this form for the linear solution. In particular, here is an example taking r equals to k equal to 0 and length of the multi-index tau equals beta. You have a decay of this form, which we'll repeatedly use for local existence and global existence. So now the idea for the proof of the lemma of norm estimates, in fact, with norm estimates, there are estimates, Dabico has one, but we didn't use it because it was more concentrated on the asymptotics to time. neglecting the constant since he doesn't have these epsilons like we do, and we are interested in behavior of epsilon as it goes to 0, so we didn't use that. There was one also, linear estimate of Pino and Chen, but the spaces are not suitable for our own problem. So we decided to go back to Matsumura, and we made some modifications to his work. So it's a long one, but I'll try to point out some of the important modifications we made. So at the start, we have here the norm of the function in L2. We know that it's less than or equal to the norm of the Fourier transform. You have equality only if the function is in L2 intersection L1. That's the Plancher. So the next equality comes from definition of the Fourier transform, and we separate the right-hand side into 4 parts. We do this to separate the frequencies. I've mentioned that the solution has a low frequency part and a high frequency part. And in our case, or maybe usually, the most troublesome parts are the high frequency parts. So I give an example of how we handle one, which I call I1 here, which is defined as this, high frequency and the terms in the integral. Now, following the solution form we've seen before, we can bound this fundamental solution U1 in the Fourier domain as this. Now, K can be 0, 1, or maybe more, but we are only interested in K equals 0, 1, since we are dealing in U and its derivative. So we put this bound into equation 16, and we reach here. So now we're with Matsumura's estimates and our modifications. Mostly it's about balancing some terms of interest that could behave terribly at high frequency. So we balance those so that we can extract epsilon explicitly and see it, because we want to know how the constants behave when epsilon goes to 0. So in this case, we have from the second equality here, we have a balance. You see the first inequality, you had 2 epsilon to the power of 2 into k minus 1. So we take a factor out of this first inequality, a factor of epsilon to the power of k minus 1, and we take it inside the integral. This is one of the first steps of our balancing act. And you notice in the first inequality, we had a frequency to the power of 2, then to the power of 2, then length of the multi-index. So for this one, we add a power plus k minus 1 also for balance, and we add that power in the denominator. So now we claim that, or we proved actually, not only claim. So now this term will extract it with the SOAP in the high frequency. And how we analyze it is that, of course, if the frequency is high but less than or equal to some m, then for fixed epsilon and beta, you are still in a compact domain, and a continuous function will be uniformly bounded. Now, the problem is when this frequency is so high, greater than or equal to NM, you can take maybe. So this is where issues can occur. So we analyze in the asymptotics. We see that for large frequency at the top of the term in the brackets, the square root of 4 epsilon, absolute value of eta to power 2 beta minus 1 will be dominant. So we take it out to power 2k. Down below, we leave it as it is. Now we take the 2 in the power, and you'll see that we have a factor in the numerator looking like a factor in the denominator. Ultimately, this will cancel out, and we'll be left with a factor of eta to power beta minus 1 into k minus 1. So here we make use of the fact that our beta is less than or equal to 1 to get a bound for this one. On the right-hand side, this is the definition of our fractional Laplacian. So a definition of the norm in hk minus 1, as we've seen from the start, thanks to Plancherel. So the same thing applies. The next term, we define it as such. Now it's in an annulus. And here you notice that we have a different bound for the fundamental solution in this annulus. So this is how we treat them. I1, I2, I4, we all have different bounds. And we try to control things where we see potential issues. So looking at this bound, in the second case, we see a potential issue for when the denominator in the 1 plus absolute value of sine goes to 0, because left end of the annulus can allow that. So we don't want such an increase. So in this case, we balance. We know that sine theta over theta goes to 1 as theta goes to 0. So we balance the input of sine here, and this is one of the first places where a factor of 1 plus t is extracted in our proof. So we do similar estimates for I2, just like I1, I3 also, different bounds. Here, this is at the low frequency for both I3 and I4, so we don't have much problems here, and the result is totally fine, just as in Masumura's. So for the local existence now, which I go to the idea of its proof, we have seen the results that for 2 less than p less than some n over 2 betas. Allow me to go back here. This is the theorem. We wish to prove that there's a unique mild solution, which means a solution written in a Volterra integral form. So as I said before, the local existence argument is by Banach contraction principle. And I'll give more details because it's the exact argument for global existence. We just need to change the space. And we refer to lemma in Daibico and Fino, and that's it. So for the local existence, we define the ball like this. We've seen this constant depending on epsilon. We have seen something similar in our norm estimates. And we define the norm of the ball as such. So what we have to do here, we have to show C is continuous in time, it's differentiable in time. So we are looking at doing 2 things at once. So we'll go with vector form. We put in 2 components and we solve the issues at once. So here we define the operator chi sub u as this. S epsilon t u0, we are referring to the solution of the linear equation, but a vector now. You have ul, the first component, and its derivative, the second component. And down here is what I explained what we mean by S epsilon t minus S, which is actually a group since the linear solution exists for all time. And in this case, you have the first component is the solution, which is 0 at t equals 0, and it's the nonlinear term at t equals S, sorry, not 0. So this is in line with Duhamel's principle, where you get the nonlinear term down into the initial conditions and you shift the problem by time S. So the first thing that is required from the Banach contraction principle is that the domain on which we are applying this argument should be invariant. So this is what we are after. We take an element u in the ball. We apply the function chi. The first inequality is the triangle inequality. The next ones come from the definition of the norm. That's the equality. Then the third inequality, the first time comes from our decay estimates. We have 1 plus t raised to the power of some negative power for ul and ul of t. So we can throw it away here. And the next term, we switch integrals because our nonlinear term, we can write it as actually a Riemann-Roube fractional integral of order 1 minus alpha. Switching integrals, we can integrate in the second term in the norm, and we'll arrive at this value, which is t minus sigma to the power of 1 minus alpha in the integrand. You have a norm of u sigma to power p in L2p for the function. So at this state, we apply the Sobolev embedding theorem here. If n is 1, you have the exponent restricted in the interval from 2 to infinity. And if n is 2 or 3, you have also this restriction. Finally, we reach this inequality right here, which is about the invariance, and this is where we choose the radius of the ball for local existence. Clearly, this radius will depend on time, and we'll see in contraction that time will have to be small because we also want the contraction property for the Banach contraction argument. which is next in line actually. So the meaning of contraction is that if you take two elements in the ball, the distance between the difference of two elements is squeezed by the function after application. So we start here as such. This is the first inequality is by definition, actually. The first two terms are solution of the linear term, which is unique for the same initial data, so they go. Then the nonlinear term, since it's an integral with the singular kernel and so far, you can still retain linearity. You have a term of this form. And we reach here, just like we did in the invariance. So in this case, for contraction, I keep some inequalities here. They will be used in, it's the same argument for the global existence, just some changes to the space. So I keep this inequality for the first one, looking something like Minkowski inequality, but not quite. The second one is a mean value type inequality, which we'll use since we have a difference of solutions as the input of our integral term. The next one needed for the contraction is the generalized Holder's inequality. So these are all applied, and eventually we reach an inequality of this form after all these treatments of the nonlinear term. So here once more, this is from the first inequality to the second. This is where the Minkowski type inequality works, and you reach here. Then after the Minkowski type inequality, then the Holder's inequality. Then you reach the final inequality here, where you see again time is appearing on the left, and we'll have to choose everything less than 1, not being too specific. This is the smallness of time, and we see that time depends on the initial data here. So that chi is a contraction. And so you have a fixed point by the contraction mapping principle. And by extension, you have a mild solution because it's defined in the integral form. It's differentiable since you use the vector form to handle everything at once. Then next is the uniqueness. We want uniqueness because we are interested in long-time behavior. We have to track solution trajectories. And eventually, we don't want to be tracking, and then we find that trajectories intersect. So we need uniqueness. So for the uniqueness, we'll put it in the form of Grunwald's lemma, as stated before, with G of t being the difference, U of t minus V of t in the norm. And H of t is the singular kernel t minus S. For the choice of alpha less than 1, H of t will be in L1. This we have already shown is continuous into H beta, this difference. However, we are missing a constant we mentioned in the Grunwald's lemma, C1, which is a product of, allow me to reach back. Yes, we are missing the C1 here, which multiplies the exponential. In our case, C1 is 0. So everything becomes less than or equal to 0. And we have our desire by Grunwald's lemma. So the next is the global solution. Here I put in the first few lines of the slide the decay estimate of the linear solution to keep reminding us of the importance of norm estimates to this argument. And this is our main theorem of today for the global existence. We see that if our exponent of nonlinearity P is greater than or equals this value, and if the initial data is small enough in the sense that we have some delta greater than 0, such that the initial data in the product space of the chosen function spaces for phi and psi is small enough. And here we also require L1 for the small enough. We need some decay for niceties. Then we have a unique mild solution up to infinity. And the behavior of this solution at infinity, the nonlinear solution, the decay is different. As you can see, if you compare 22 with 24, you have a loss of decay due to the singular kernel and beta here. So this is the effect of the non-local nonlinear term we've chosen. The alphas appearing and losing decay. So like I said, all of the arguments now are the same with the local existence, but will only make corrections to the space. Then that's it. Everything is applied the same. So we define our space as before. X here is the space of continuous function intersection C1, but here time is to infinity. We are handling global solutions, and we define our norm as such. The norm is different from before. We take our time here and we put it inside the norms with appropriate decays. We define the norm of U in X0 like this because we want some tight bounds. We have already seen the norm estimates of the linear solution. And by that, since you are losing decay, then the linear solution is in X and you can have it in some ball. Here we start the argument for the contraction principle in this ball like this. But eventually, since we said the initial data is less than or equal to delta, we can have a ball independent of initial data. The radius is already independent of time. So we can have it also independent of initial data, thanks to the problem of global existence being similar to stability for the trivial solution. In this case, now, since we have U in X, we don't have to bother. We already have our decay. The linear solution exists for all time. So the part of the solution that could present us some potential problems is the integral part like this. So we define our operator on the ball as such. As before, we'll prove that the ball is invariant under the action of the operator lambda, and we'll show the contraction property. Though, as before, now, there's a difference. The difference here mainly is that one, this proof idea is for beta not equals 1. Because for beta not equals 1 and beta equals 1, the difference is that we have a fractional Gagliardo Nirenberg inequality that is imposing on us that the global solution only holds for n equal to 2, 3 if beta is not equal to 1. But for beta equals 1, we use the usual interpolation inequality, and it does not restrict us. So, but the proof is exactly the same. It's still the same fixed point argument. So, as before, this is the operator. J is equals to 0 or 1. I'm handling U. It's the same for the derivative. You have this by the definition. Then the second inequality comes from the decay we have for the linear solution. And now this last inequality is actually a lemma in Fino's work and Dhabi's work. So you have to just check the exponent, n over 4 beta plus j over 2 equals 1 or less than 1, and so forth, and just substitute. And the decay will come out exactly as we predicted in our problem. The term 1 plus tau raised to the power minus pn over 2 beta 1 minus 1 over p is coming from how we handle the fractional integral. Because at first, the norm of the solution from first inequality, you'll put the fractional integral in L2 intersection L1. Now, putting it, since it's an integral, we can extract the integral 0 to s and the singular kernel out. So we are left with the u to the power and u ln. But ln of 1 plus absolute value of u is less than or equal to absolute value of u. So you have p minus 1 and u inside. And then applying the L2 norm, you'll be left with norm of u in LP inside and norm of u in L2 plus p. So the term with 1 plus tau raised to the power minus pn over 2 beta and the brackets 1 minus 1 over p, it comes directly from this interpolation inequality that we obtain for our space X0 with the space LP and L2p. So Now for contraction, because after this step, everything is the same as before with the lemma of Pino. For contraction, we'll still need holders inequality. We have discarded Sobolev's inequality in favor of interpolation inequality, but holder still remains for contraction. So in this case, we have the difference, and by definition, we have this. Then the nonlinear term having the terms of u to power p minus 2, u and the ln minus v to power p minus 2, v and the ln is because of the linearity of integrals. We treat it as before, like I said, we apply the norm estimate for linear solutions. We have this. Then now what I call W is the difference in the brackets before. And we treat it exactly the same as U. We have the interpolation inequality. From the interpolation inequality, we reach the holders inequality, and that's it for us. We are done. Exactly the same calculations for the derivative in time, and lemma 1 in the work of Pino and Dabiko gives us all the case that we want. I should mention that this work, if you apply beta equals 1, the calculations work exactly the same. And our theorem for beta equals 1 is the same as that of Dabiko's work in the influence of nonlinear memories. So it's an improvement on the global existence problem of Fino, because Fino couldn't cover the entire supercritical range for the global existence, and ours does that. And here brings me the end of this. Thank you so much. I hope you enjoyed this talk, and